clever. But you guys have, or we have, this pumpkin farmer who the cops are like, oh man, this dude totally speeds on this stretch of road. We're going to catch him. Motion is continuous and differentiable. Why do I make a note to tell you that? What's the big deal about it being continuous and differentiable in this section? What's the theorem that we're talking about? Forever card number, what is it, 20? Is that right? Okay, forever card number 20 is one of the cards, the last card that we did, and it's mean value theorem, good, MVT, and MVT says if a function is continuous on what kind of interval? Closed, endpoint to endpoint, good. If a function is continuous on closed endpoint to endpoint and differentiable on open, just in between. Wait, what's differentiable mean again? Able to be derived, aka the derivative exists. Some of you got stuck in homework last night because you weren't quite sure what to do with that whole derivative existing thing. And the derivative exists. Sorry, I was just checking on one of the alumni that I know. Then MVT applies. And what does MVT say? If a function is continuous on the closed and differentiable on the open, then there exists an x equals c where? In between a to b, such that is equal to? And what's another way of talking about f prime of c? Isn't that also the instantaneous rate? So we could say by MVT, since motion is continuous and differentiable at all times. Okay, since motion is continuous and differentiable at all times, meaning it will be continuous on the closed and differentiable on the open because it's continuous and differentiable everywhere, then let's go ahead and apply the conclusion to this problem. We could say f prime of c, but we don't even have an f of x. We could say the farmer's instantaneous speed, aka what's showing on his speedometer, his instantaneous speed must have been, aka f prime of c, his instantaneous speed must have been, what's that formula? F of b minus f of a all over b minus a. How can we do that from the formula, or from this, I should say, scenario, if we don't even have a function and we don't even really have time a and time b? What do we know? Yeah, we know that the posted speed limit was 55. We do know they're 5 miles apart. What was he doing when he first passed the cop? 50. He's going 50 to begin with. What's he going when he comes back again? 55. What's the one piece of information I missed? 4 minutes. So it's like, oh, hey, at this time, when he passed cop A, he was fine. When he passed cop B, he was fine. He was even waving, being like, it's a good day, right? But what can I do with this information? Can't I figure out his average rate? How do we find rate? Isn't it distance over time? Miles per hour? Wait a minute, 5 miles per 4 minutes doesn't work. What do I need to do? Yeah, build a bridge, good. And my bridge is going to get rid of the minutes, so it's going to be 60 minutes per 1 hour. How fast was he going? If his average rate was 75, double check my math really quickly. 4 goes into 60, 1 and 2, 15 times, and 5 times 15 is 30, and 60 and 75. I think I'm right. Who made it? Oh, I thought it was one of my kids that was gone. Thank you. Hi, Andrew. Bye, Andrew. 75 miles per hour. So, could they give him a speeding ticket? I don't know. I don't know if California ordinance allowed them to give him a speeding ticket, but do they know he was speeding? Yes. So what do they need? Probably a very hidden calculus cop C in between somewhere to catch him. But does the idea make sense? right? But he was going 50. He was going 55. Oh, yeah, but to cover that distance in that amount of time, he had to be going way over 75. But if he went an average of 75, the long story short is, did he have to speed at least once in between that interval? Yeah. The farmer's instantaneous speed must have been at least once, and probably a lot more, and probably a lot higher, once in those 4 minutes. So we're not going to go ahead and talk about the law and whether or not they could actually get him on that very solid mathematical evidence, but they're just trying to go ahead and have you guys think through MVT in a very practical example. Does that make sense? It's a good thing most cops don't use calculus, because I don't know about you guys, but if I see a cop, I typically slow down at least a little bit. Right? Anybody live in Simi? Oh, they have rough cops in Simi. Whew. I haven't got caught by them, but I've heard. They just like stay and camp out and wait for people to be coming down that hill just a little bit too fast. And anyway, yeah, Simi's rough. Was this a homework problem last night? No, it wasn't. Was that one? No? Okay. Let's go ahead and, you guys have your notes open. Let's do a few more MVT examples. And let me try to get a couple rough examples also, because I think some of you guys, it wasn't so much that the idea was hard, hopefully, but I think maybe you just didn't like some of your derivatives. What do you guys say? Everything. Continuous, no holes, no breaks, no jumps. Differentiable, no holes, no breaks, no jumps of the derivative. Like, you have a forever card to memorize, so hopefully not everything. There's a forever card, MVT, and we just said it like 5 times today. And I'll keep on saying it. We know it's MVT. We need to maybe get a little bit more perseverance, grit, willingness to persevere through. Some of you just kind of have mental blocks whenever you see words. Guess what? There are words in calculus, so we're going to have to keep going. What's going on here? A plane begins its takeoff at 2 o'clock p.m. on a 2,500 mile flight. After 5.5 hours, the plane arrives at its destination. Explain why there are at least 2, what? 2? At least 2 times during the flight when the speed of the plane is 400 miles per hour. Think about the story. Some of us get way too stressed when we just say, this isn't exactly the example we did in class yesterday. Guess what? They never will be. They will never be exactly the same example. There are way too many numbers in existence, an infinite number, actually, for you to ever see the same exact problem twice. So get out of your head that you're going to see the exact same problem and say, okay, what's the idea? What's the idea? We just talked about a pumpkin farmer that had a rate, how fast. What do you guys see up here? I see hours and I see miles, don't you? So what can we do with those miles and hours? Yeah, I like that idea. So Nick is thinking about the average rate, and an average rate, you do change in distance over change in time. And so what's the change in distance on this flight? 2,500 miles. And what's the change in time on this flight? Yeah, 5.5 hours. All right, cool kids. What happens when you divide those two? This is the first time I don't have one kid who always has their calculator out. 2,500 divided by 5.5, 454.545. Okay, think through mean value theorem. Motion is both continuous and differentiable. Think through mean value theorem. Motion is both continuous and differentiable. And with mean value theorem, how do we have the answer? Excellent logic. Now, how do we use the math to say that? What would guarantee that? Motion is continuous and differentiable. We could do it 2 ways. One way is by IVT and one way is by MVT. One way is by IVT and one way is by MVT. Actually, I think we both have to do MBT for both of these times. So let's go to MBT. By MBT, since what has to be true for MBT? Since motion is continuous and differentiable at all times. So I'm not stressing about the open and closed thing because motion is just good everywhere. Since motion is continuous and differentiable at all times. And the average rate of the plane is 2,500 divided by 5.5. So you didn't even have to do the math, but knowing that it was 450 kind of helps. Since the motion is continuous and differentiable at all times, and the average rate of the plane is 2,500 over 5.5 miles per hour, aka 454, the plane must have gone that speed at least once in the journey. Now hold on, what have I proven so far? The plane went at least once. Good. Now, take Nick's logic. How do I finish the problem? So far, all I've said is the plane had to have gone 454.545 miles per hour at least once. How do I take it home? What theorem guarantees what Nick was saying that said, well, if you go from 0 to 454 and 454 back to 0, what theorem says, oh, hey, there's a guaranteed in-between value? Then, by IVT, since by IVT we need continuity, so we can say motion is continuous. The plane had to go 400 miles per hour at least twice. As it went from 0, you could say, at least twice between takeoff, what did it say, and touchdown? Something to that effect. We could have worded that a little bit differently. But the idea is by MBT, we know that it had to have gone 454, and then by IVT, well, if it had to go 454, and it starts at 0 at takeoff, and it goes back to 0 at touchdown, well, therefore, it had to have gone between the lowest, 0, and the highest, 454, at least twice. Now, this is a nasty problem as far as explaining. And I was very detailed in my explanation because the AP guys don't just want to know that you know what to use by MBT or by IVT, but also the ifs that need to be true and that they are true before you say the thens. But MBT says, yeah, it had to have gone this fast, and IVT said, okay, then fine, it had to go up through 400 to get there, and then back down through 400 to get back down to the touchdown when the plane arrived back in. Now, what's going on this one when we see this graph? Yeah, it's going to be some sort of piecewise function, at least it looks like one, right? But they don't tell us the whole thing. Well, that's nasty. But they do tell us in the beginning that the figure shows two parts of a continuous differentiable function, and then the derivative is also continuous. So the original function is continuous and differentiable, the derivative is always continuous. So even though we don't see the whole thing, we know that stuff is missing. They're asking us, why must f have at least one 0? What could you use to defend that f has to have a 0 somewhere in between the beginning and end, even though we have no clue what's going on in the middle? What theorem would guarantee that the function has to go through 0 at least once? IVT. Good, Ryan. Because what do you see the function, or where do you see the function over here in between like -10 to -8? It's above. And where do you see the function over here in between 0 to 4? It's below. Well, to go from above to below, IVT, if this function is continuous, which they say it is, what's it going to have to do at least once? Cross through. Can it do it lots of times? Yeah, but at least once. IVT, we could use the actual definition of the theorem, but that's okay. Just keep going. Letter B says, explain why f prime must also have at least one 0 in the interval. Ooh, how can I say that? MVT would say, take this point to this point and find that slope. But here's the problem. Is that slope 0? No. Well, I could say for sure it's going to be negative. I say for sure it's going to be 0. Not answering, I'm just giving you an idea. Tangent lines. What's the sign, positive or negative, of that tangent line? What's the sign of that tangent line? Who sees it? A positive tangent line to a negative tangent line? There needs to be a min or max because it says that the original function is continuous and differentiable, no sharp points. If there are no sharp points, how else can I go from a positive to a negative? What theorem, though, helps me out with that? Not MBT. MBT says here to here. Well, that's not 0. Why does IVT prove it? I can say if the derivative is positive at one place, if the derivative is negative somewhere else, what had to happen in between if the derivative is continuous? Oh. The slope had to be 0 because, guys, wait, just think of numbers, right? If the derivative is positive and it somehow goes, what does it have to cross in between? A 0, right? If the derivative is a positive and it goes to a negative, it has to cross through a 0. That's just IVT again. But it's IVT with f prime. Because f prime is positive, f prime is negative. Well, then there had to have been a place where f prime was 0 because he's continuous also. This one was with f because this one, f was all these y values. F was positive, all these y values. F was negative, so f had to go through 0. And then letter C says, make a possible sketch of the function with 1, 0. Let's not worry about that right now. That's messy. I don't like that one. It's very imprecise. Okay. With that, I want you guys to peek and see. Some of these are like AP type questions, and they're good and all. I want you guys to look for functions that were similar to homework last night that you didn't like, okay? Because you got stuck on some homework problems last night. And I'm curious what was going on. Did you have fractions? Did you have product rules? What kind of functions did you not like with MVT? Or rules, either one. Go ahead, you can look in your homework spirals. What kind of ones do you get stuck on? Because the idea is pretty basic. Is the function continuous? Is it differentiable? Are they asking about roles? Okay, fine. Does f of a equal f of b? Okay, to test. What ones didn't you like? Is it a fraction? Is it a product rule? Is it a chain rule? Find one you didn't like and tell me what the function looks like. Okay, what's one that you guys didn't like? Allie. Oh, so it had some nasty things in it? Okay. What else didn't we like besides 56? Okay, let's start with 48 because that one no one was able to look at a calc chat for. Does that sound good? So with 48, we're in homework 3A. Let me just go ahead and get a nice little piece of white space. All right, kiddos. What were the directions? Find C. Okay. So determine whether it can be applied, find all values of C. Let's start with 48, because all of us are maybe equally, or we're not quite sure if we're right. What was the function for 48? Like that? Is it just x plus 3 with no parentheses? Oh, I thought I heard plus, sorry. Okay. Continuous. On a closed interval. How do we do that? We have to think about domain. What's the domain of an ln? Because he's not a problem, but he's a problem. Domain of an ln, what has to be true? Good. This has to be greater than 0, so x has to be greater than -3. Are all my values greater than -3? Yes. Do we know what ln looks like? Are there any sharp turns in an ln? And if you multiply by a polynomial, no sharp turns. But actually, we don't even need to worry about sharp. We just need to ask, does it exist? Well, if the domain is greater than -3, yeah, it exists. It's fine. So therefore, we can say, yes, it's continuous because the interval is greater than the domain restriction. Good. Number 2, differentiable. On negative weight, differentiable doesn't need to be closed. What's it allowed to be? Open. Differentiable, able to be derived. Did you guys realize? Just take the derivative and see if you can derive it. We have to take the derivative anyway for MVT, so why don't we take the derivative when they're asking, is it able to be derived? Well, I don't know. I'll go check. So when you come and check, second, first, plus first, d second, wouldn't that be 1 over x plus 3 times 1? Derivative of ln of u is 1 over u times u prime. Are we okay? So then don't we end up with, I believe, ln of x plus 3 plus 1. How's that look? According to last night. Okay, any questions on the derivative? Second d first plus first d second. And the derivative of ln of u is 1 over u times u prime. Now, if you're not getting these derivatives right, we're in some serious. You have to be able to do the derivative or else you're going to be stuck. So you guys need to be asking some serious, reflective, introspective questions. Why am I getting derivatives wrong? And if there's a reason for it, or if you don't know the reason for it, come in and let me know. My question, what's the domain of f prime of x? Any problems with this guy? Just the ln, right? So isn't that still just x has to be greater than -3? Oh, and that is greater than -3. The open interval is, right? Guess what? Able to derive. Now, did you catch that? Some of you got stuck on how to do continuous and differentiable last night. Differentiable, find the derivative and say, do you exist? The answer is yes. Okay. Continuous check, differentiable check. So then what do we do? If number 1 is true, and if number 1 is true, then what do we say? Yeah, good. There exists an x equals c within A to B such that what? F prime of c, can I just steal this guy? ln of x plus 3 plus 1 equals, okay, careful, don't forget, what's the rest? F of, who's b in this example? Minus f of a, which is -2, all over, does that make sense? B minus a? How do you solve for c? Well, I have to get the special x and make sure it's in between. Don't we just have to plug in? If I plug in -1, I think I end up with 2 times ln of 2. You guys agree? If I plug in negative 2, I end up with ln of 1, which is 0 times something. But negative 2 plus 3 is 1, and ln of 1 is 0. All over negative 1 plus negative 2, that's just 1. Oh. Now careful. 2 ln 2 isn't my answer. I still have to solve for what? Uh-oh. Uh-oh. What do I have to solve for? You guys should know this. Solve for who? X. Because x, c is a special x, so solve for x. 2 ln of 2, that's gross. I know. Technically, we could make it a little bit nicer. Couldn't we make it ln of 4? Could bring that 2 up and make it ln of 4 if that makes it any easier. We're going to have ln of x plus 3 equals ln of 4 minus 1. I'm going to put little parentheses so we don't think that that's ln of 3. It's not. Minus 1 is separate. I can do e to the on both sides to get rid of the ln. And I'll end up with x is equal to negative 3 plus, I have to subtract the 3 to get to x, e to the ln of 4 minus 1. Now some of you are like, well, that's great and all. I'm pretty sure that doesn't fit in the interval, so therefore none? Because negative 3 plus something? Well, wait, negative 3 plus something. Maybe it does fit in the interval. How can we figure out who this guy is? You guys remember what subtraction in exponents signify? Division. So we could actually make this negative 3 plus e to the ln of 4 over e to the 1. E to the ln of 4 minus 1. Why is that nice? E to the ln of 4, isn't that just 4? Four is 4. E is 2.71828. 4 divided by almost 3-ish. Isn't that 1 and something? 1 and change? What's negative 3 plus 1 and change? Does it fit? Negative 3 plus 1 and change, 1 point something, something, something. Does it fit? Yeah, because it's going to be a little bit up beyond negative 2, right? Negative 3 plus 1 is negative 2. But I set in some change, so then go a little bit more up. To be honest, we were right. Now, pause and help me out. Where did this problem get hard? AJ, you said something. Where does it get hard? Okay, so derivatives got hard. Okay, so some of you guys, maybe ln of u got a little bit hard. Where else did it get hard? For someone else. Ale. Okay, yeah. That was messy, right? That was messy. Could you have stopped like here-ish and plugged it in your calculator and seen if it was a decimal that worked? Yeah, and you could have just boxed it. That's okay. That's okay. But remember, when you're solving for x, the function has to be set equal to f of b minus f of a. Pause. Was this rolls? Forget the directions. Was this rolls? No. How come? Janelle, do you remember? What would be special that would happen to make it rolls? So what would have happened here when we tried to subtract? We would have gotten 0. Yeah, and we didn't get 0. So we knew it wasn't rolls, but whatever. We can still use MVT. Dun, 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 dun. Yay. Okay, you guys also asked a question about one more. I think I can do one more. We're going to go ahead and grade the evens tomorrow. Why are we grading the evens tomorrow? Because all of you were hopefully able to attempt this homework, but does that mean that you perfectly got it? No. Since you didn't perfectly get it, that's totally fine. I went over some extra examples today. I needed you to get into homework and fully try it, so that way you can come today asking me questions like, I don't know what to do when, fill in the blank. Okay? I need you to go back and to finish this up. Now, we are kind of peeking at section 3.3 in just a few minutes to get an idea of what's going on, but we'll grade the evens tomorrow and finish up homework questions. But if you don't go back through homework and try to go a little further, a little deeper, a little better into problems, you're kind of wasting time. Does that make sense? Take today's class, take the answers that we've gone over or the questions that we've gone over and try to apply them to the questions that you had, okay? I heard that one Ale was saying with the ln and the secant. Is that where you want me to go? Okay. Guys, you are going to have ones with fractions. You are going to have ones with fractions. When you get to ones with fractions, just because I'm going to do the ln and secant one, when you get to ones with fractions, I want you guys to think, where was it? Kind of that one. Kind of back into this one. Absolute extrema. Didn't you guys have some nasty fraction ones that you had to deal with? Like maybe where we had something like this and we had to get common denominators in order to start thinking about a function. Or maybe something like, not that one. Well, yeah, this one we got common denominators too. It made it prettier. Or maybe over here when we were doing critical numbers. Remember how we did the green trick to factor out what was in common? All of those things are still true as far as how to get a derivative simplified. If you notice, kind of, hopefully, still the hardest part is how to get the derivative simplified. It's not even so much the concept in applying it, hopefully. It's not even so much the concept and how to apply it, hopefully. Hopefully it's more the derivative simplified that's hard. So let me go ahead and let me get rid of that one. All right. Ali, what was that one that you said? Number 50? 56. Okay. Is it the same directions of MVT and find C? Cool. What's my function? Hey guys, what derivative rule am I going to use? Not products, there's no times that I see. You have to be able to read the function. Read the function. ln of, that's not times, right? That's chain rule, that's matryoshka. ln of secant of, does that make sense? ln of secant of. Ooh, how many matryoshkas do I have? So if you're this kind of person, you could say, okay, so my f is equal to ln of u, my u is equal to secant of v, and my v is equal to pi x. If you're that person, there's your f and your g and your h. How do I take the derivative of 1 over u? Sorry, of ln of u. My bad. Wait, the absolute value, it's okay. Look at your forever card. It's the same thing. It's still just 1 over u. Times. Derivative of ln of u is 1 over u. Just keep the whole thing. Times. Okay, now it's time to peel off ln. Whose turn is it? What's the derivative of secant? Secant of times tangent of. I haven't changed the pi x yet. I'm not allowed to. Now it's time to deal with the pi x. Chain rule. You have to multiply. Don't kill those bunnies. Times pi. So we end up with, wait a minute, what happens there? Nice. So we end up with tangent of pi x times pi. Okay, now hold on. We haven't done some work. We did the derivative. This would technically be a part of step 2, because we're trying to figure out whether or not MVT applies. We figured we needed the derivative, so we started there. But step 1, technically, of our ifs is f is continuous on endpoint to endpoint. Okay, what's the domain? Well, for ln, this needs to be greater than 0. Oh, wait, absolute value. Huh. Doesn't have to be greater than 0. Forget that. But secant can't equal 0. Uh-oh, we better figure out when secant equals 0. Wait a minute. Can secant ever be 0? Because I can't divide by something and make it 0. Okay, well, forget that. That's not a problem. Secant can't be 0 anyway. Secant, though. Secant has vertical asymptotes. So my ln is fine, because that can't be negative and it can't be 0. But my secant, now I have some issues, because secant is 1 over cosine. Can't cosine not equal 0? If cosine equals 0, then secant doesn't exist. Okay, stink. When does cosine equal 0? At pi over 2 and 3 pi over 2 and 5 pi over 2 and I need this inside piece to never be pi over 2 or 3 pi over 2, or this interval is not very big, so I'm not stressing out about having a lot. But guys, what happens if I divide by pi? Don't I get that x doesn't or can't equal 1/2 and can't equal 3/2 and can't equal 5/2? Are any of secant's vertical asymptotes going to happen in between there? 1/2 would be a problem. 1/2 would be a problem, but he's not in that interval, so I'm actually totally okay. So I looked at ln's domain restrictions. Nothing could happen between 0 and 1/4. I looked at secant's domain restrictions. No vertical asymptotes will happen between 0 and 1/4. So guess what? Whew, continuous is true. Number 2 says f is differentiable, which we just found our derivative. Aw, stink-a-dink. Are there any domain restrictions of our derivative? Tangent. Oh, tangent has vertical asymptotes. Aw, stink. Do you guys remember where tangent has vertical asymptotes? Pi over 2. Okay, stink-a-dink. So then my domain of my derivative, tangent, can't equal pi over 2, or can't be at pi over 2. I should say, I apologize. Tangent can't be of pi over 2. So my pi x can't be pi over 2, or technically 3 pi over 2, or negative pi over 2, but there are no numbers. I'm going to divide by pi. Wait a minute, doesn't that just still happen at 1/2 and 3/2? Oh. Well, that's not in the interval either. So guess what? Differentiable. Check. So what am I doing? I'm having to go back to basic graphs and say, when does secant not exist? Ooh, at pi over 2 and 3 pi over 2. Let's make sure those x's, this pi x can never be that. Oh, it can't. When can tangent not exist, or when does it not exist? Ooh, can't equal pi over 2 or 3 pi over 2. It doesn't in that interval. I'm good. So then the end of the day, I can say then there exists. It's like the 10th time today I've quoted MBT. And x equals c in between who and who? A and b, so my 0, 1/4, such that, okay, where do I go? What's my formula? Be careful, not f of, f prime of. Good, so take your prime. Has to equal what? Good, f of 1/4 minus f of b minus f of a all over. So we have to solve for x. To do that, we have to go back to the beginning and say, you kidding? I'm like, sorry, no. ln secant of pi over 4, 1/4 pi, minus ln of secant of, well, 0, all over 1/4. I don't know, secant of pi over 4. Oh, come on, it's a 45, and it's 1 over cosine. Maybe eventually we could get to 2 over root 2, which ends up reducing and rationalizing to root 2. Secant of 0, 1 over cosine of 0. That's 1. ln of 1 is 0. ln of root 2, I don't know about you guys, but I think that's 2 to the 1/2. I can bring down a 1/2 power. I'd flip the 4. I'd have 4 times 1/2 of ln of 2 equals pi tangent of pi x. Ugh. That'd be 2 ln of 2. That'd be ln of 4. I guess I could divide the pi. Tangent of pi x equals ln of 4 divided by pi. Moving that guy. How do I get to x? Tangent inverse. This is not unit circle, everybody. And divide your pi. You could do tangent inverse of both sides and then divide the pi. You might want to go to your calculator and make sure it's in between 0 and 1/4. Sadly, my little phone calculator won't cut that one. But I think, man, I gave you way too much of that problem. However, it was really nasty to solve. I totally agree. You guys might want to double check that and make sure that it works. I did it really fast, so there could be a mistake, but hopefully that helps you in homework in one way, shape, or form. I want you guys, though, to see the beginning of section 3.3. I want you guys to see the beginning of section 3.3, because after MVT and rules, you might be like, I hate this thing called calculus. Really, it's derivatives. You can hate derivatives. Don't hate mean value theorem. He's really nice if the function's really easy. But things are usually hard when the function's hard. But 3.3, remember, all of chapter 3a is like, hey, let's figure out characteristics of graphs. So 3.1, absolute extrema, quick introduction to relative extrema. 3.2, there's this thing called MVT that guarantees the function goes through different places. Section 3.3, let's talk about how a function can go down or go up. That sounds easier, right? Let's talk about how a function can go down or go up. We did something like this in pre-cal, where we would label branches of the graph and say, he's increasing, he's increasing. We even talked about how to label this with intervals and say, hey, he's decreasing on, we could call this A and call this B, on negative. And he's constant from A to B, and he's increasing from B to infinity. In pre-cal, we just talked about how to look at a graph and explain what's going on with intervals. In calculus, we don't get the graph. We have to figure out where this happens from the function, but it's all possible by derivatives. It's all possible by derivatives. You guys don't need to write all of these words down below as far as the definition of increasing and decreasing. Let me show you the long story short. If a function is increasing, that means if x1 is less than x2, then f of x1 is less than f of x2, meaning as the x's get higher, the y's get higher. If a function is decreasing, as the x's get higher, the y's get lower. And the long story short of all of that is like, wait a minute, hold on. I know another way of thinking about this. Instead of having to see a graph and having to see this whole branch where it's all going down or all going up, don't we have something called a tangent line? And won't the slope of the tangent line seem to indicate the behavior of what's going on of the original? For all of these decreasing pieces, aren't the derivatives negative? And for all of these increasing pieces, aren't the derivatives positive? I wonder if there's a way where we could figure out all the in-between points, all possible points where derivatives could change signs, or all possible points where the function's behavior could switch, and make something called a sign chart, pre-cal, make something called a sign chart and split this up into its different intervals, and know just based on whether the derivative is positive or negative, when and how and where the function is moving and changing. Now, we're not going to get to all of this today as far as writing down notes. I just want to give you guys a conceptual understanding of what's going on. Without looking at a graph, we can tell by the derivative sign whether at a point the function is increasing or decreasing. And that's great and all. At a point if the function is increasing or decreasing. But if we split up with critical numbers, if we take our domain and split up, then we can actually figure out entire intervals where the function is going up and going down without knowing the exact graph. So guess what? Derivatives are still important in section 3.3. So practice again with the derivatives that got hard last night in MVT, okay? All right, finish up that homework number 18. Section 3.3 will get easier. Hang in there. But the derivatives, oh, you guys got to be able to derive and simplify. Keep practicing.